So the title of my talk is Nature's Rhymes. It's been said that history doesn't repeat itself, but it does rhyme. The curious thing about the quote is that although somebody definitely said it, it doesn't seem to be clear who did. It's most often attributed to the writer Mark Twain. However, you can easily find websites claiming that there's no evidence that Mark Twain ever said it. And I wasn't able to find any websites that said in that case who did make this remark. But it's an often cited remark. And at any rate, regardless of what's the case about history, physics definitely often does repeat itself, with similar structures found in many different realms of physics, often involving many different scales of length and energy, and many different types of physics. So at the beginning of my talk, I'll give one example that involves waves. We've all seen ripples of water waves on the surface of a pond or swimming pool, as in this picture. So that's a very familiar example of a wave. The distance between successive ripples is large enough that we easily see them, but in the case of light, visible light, like from those lamps behind us, the distance behind successive ripples is much too small for us to perceive, unless we're very clever about how we go about it. But in everyday life, even if we see wave phenomena, as in some details of a rainbow, we don't usually recognize what we're seeing. It wasn't clearly understood that light is a wave until experiments that were performed by Thomas Young in the early 19th century. So he was a giant figure in his day. He was the one who firmly established that light was a wave. He made the first measurements of the sizes of molecules that's generally accepted today as being correct. And he also was a pioneer in deciphering the Egyptian hieroglyphs. He didn't quite get all the way, but he got at least 60 or 70% of the way toward deciphering the hieroglyphs. And I mention that because he lived in an age when it was possible to be expert on a lot of things. Nowadays, it's usually a challenge enough to try to be expert on one thing. Anyway, in his double slit experiment, he basically gave light the chance to pass through two different paths to arrive at some place where it's observed. And he saw effects similar to the way that the waves on the surface of the pool add and subtract at different places. So that's when it was clearly established that light is a wave. Well, so there are waves in everyday life. Light is a wave. But in the 20th century, a new kind of wave was discovered that you could call a matter wave. So it was found that also an electron or a heavier particle, like an atomic nucleus, can behave as a wave. But it's hard to give a real picture showing the electron as a wave. So instead, this is a kind of computer simulation of what an electron wave inside an atom looks like. And the bright and dark spots are a little bit analogous to the ripples on the surface of the swimming pool, where the waves add or cancel. So if you study physics as an undergraduate, you'll learn about all kinds of waves. You'll learn about the equations for water waves. You'll learn about the waves that propagate up and down a vibrating string. You'll learn about light waves, and you'll learn about electron waves and other matter waves. So there are important differences between all these wave equations, but they have a lot in common. So that's an example of what I mean when I say that nature rhymes. So if you do study physics, even at the undergraduate level, you'll learn about wave equations, and then you'll come to appreciate what I've said, that the four examples I've given of waves, the waves on a pond or a swimming pool, the waves on a string, a violin string, light waves, and matter waves, all have a lot in common, although they have important differences. So there are completely different realms of physics, but there are some ingredients in common in the way we describe them. So that's what I mean when I say that nature sometimes rhymes. But there's a different rhyme that I want to talk about today. And this rhyme actually has two parts. So one part is well established, and one part is speculative. The well-established part of the rhyme is an analogy between well-established 20th century quantum mechanical laws that describe the behavior of an elementary particle like an electron, and what's perhaps the most inaccessible mystery in physics. This mystery is how to apply quantum mechanics, what's arguably the deepest theory we have, Einstein's theory of gravity, which he called general relativity. The speculative side is an extension of this rhyme in which particles are replaced by strings, possibly unraveling some of the big questions. We'll start on the more well-established side. Now, to oversimplify somewhat, and it's awkward to make such an oversimplification because Steve Weinberg, who's just published a very nice book on the history of science, is in the front row, something I didn't anticipate when I went out on a limb with this oversimplification. But anyway, to oversimplify, the ancient Greeks thought that the natural state of an object was to be at rest, and motion had to be explained. This view seemed to be based on common sense. Bodies in motion eventually come to rest unless someone stops pushing. Or at least that's our experience here on Earth. It's a true observation, but from a modern point of view, it's not simple to explain what's happening. If you kick a ball on the floor and it eventually comes to rest, what is really happening there? That's not that simple to explain. The modern view is that the energy of the moving body that's slowing down due to friction is converted into heat. And heat really consists of microscopic motion of all the little particles that make up the body and whatever it's in contact with. So that's a modern point of view, but it wasn't available when science was getting started in the modern sense in the 17th century. That, what I've just summarized here, is really a view that emerged in the second half of the 19th century. So although the observation that bodies in motion eventually come to rest if you don't keep pushing is true, it's not a very good starting point in hindsight for basing your understanding of the world because it's just too difficult to explain what's going on there. Galileo and then especially Newton made progress in the 17th century, not by understanding all that. It was still 2 centuries in the future to really understand what happens when the moving body slows down, but by identifying simpler questions that could be described by simpler theories. So Newton focused on questions like the motion of an isolated body like a planet, or for that matter, a ball moving in the air before it strikes the ground. After it strikes the ground, we have to worry about what really happens when it meets the ground. And then, as I said, it was 2 centuries in the future to understand even roughly what was happening. But as long as the ball is just moving in the air, that's something that was in the realm of what Newton could describe. Since ancient days, it had been argued that the Earth must be at rest or we would feel its motion. But Galileo refuted this by arguing that a passenger in a smoothly moving ship in a calm sea does not feel the motion. And that was the first inkling that to be in a state of constant velocity is as natural as to be at rest. So Newton redefined the problem from explaining velocity to explaining a change in velocity. The natural state of things is that a particle in motion, let's say in empty space, not under any influence, remains in motion with a constant velocity. So according to Newton, what has to be explained is the acceleration, or the change in velocity. The most elementary way to state Newton's idea is by an equation you probably all learned in high school. F equals ma. That says that the acceleration, or change in velocity, is basically determined by the force that's acting on the particle. So you can relax. That's almost the only equation we'll have. So A is the acceleration, m is the mass, and F is the force causing the acceleration. But in writing it down, the main point I wanted to say is that what is explained is the acceleration, or change in velocity, not the velocity itself. So Newton's law of motion gave a framework to determine what will happen for all times if you know what is there at a given time. So if you know where a particle is and how it's moving at some initial time, that might be, for example, today at noon, then Newton would offer to tell you where it will be in the future at any given time. So in this picture, the red ball is meant to indicate the sun. The small red dot is a planet. And the arrow is supposed to tell you the direction in which the planet is moving at the initial time, for example, noon today. And the length of the arrow tells you how fast it's moving. So Newton's initial conditions are given by the position and the velocity arrow. And then the problem that Newton defines is to predict the orbit of the planet. So it'll start out moving along this arrow because that's its initial direction of motion. However, it's attracted to the sun, so its orbit will be bent. And calculating that orbit is what Newton did. So this is what people mean when they say that classical Newtonian physics is deterministic. The whole idea is to be able to predict the future given what there is at some initial time. Now, what I've just described is an idealized problem, and in a sense that was the main idea. So as I've already told you, I didn't realize Steve would be here, but anyway, in the words of the Nobel laureate Steve Weinberg, above and beyond any specific details, the real revolution that got modern science going was, in his words, the shift that took many centuries from trying to give qualitative descriptions of everything to carefully selected phenomena where you could give quantitative explanations. So Newton didn't try to explain in detail what happens when a body slows down because of friction. Well, okay, in some idealized situations, yes. But it turns out a much better place to get started is the motion of the planets around the sun. And then there was a precise mathematical theory if you pick the right questions. Now, one thing that physicists learned about as a consequence of Newton's laws was the concept of energy. So our idealized particle moving in the gravitational field of, for example, the sun, has an energy that I'll call E. And it's a combination of two things. So one part of the energy tells how fast the particle's moving. That's often called T, the kinetic energy. And then there's another term, V, that tells how far the particle is from the sun. So the energy, okay, this is almost our last equation. The total energy is the sum of an energy due to motion and an energy that has to do with where you are in the field of the sun. So the great thing about it is that as the particle moves, its total energy doesn't change. T and V change, but the total energy does not change. So this is a schematic picture of a planet going in an elliptical orbit around the sun. When it's close to the sun, it's moving fast, so its kinetic energy is bigger. But since it is close to the sun, its potential energy is less. As it moves farther from the sun, it slows down. Its kinetic energy is less, but its potential energy is bigger. So anyway, the great thing about the energy is that it's a constant. And that helps you understand the motion of the planet. Now, for a long time after Newton, the framework of physics consisted largely of refining and polishing what Newton had done. But in that period, people came to understand Newtonian physics far better than Newton had. And some of the things that were discovered were very important afterwards. And I'll just tell you about one, which is that 18th century physicists discovered a remarkable thing called the principle of least action. So in the terminology that physicists usually use in practice, Euler and Lagrange usually get most of the credit, along with de Maupertuis. But apparently the first glimmering was by Gottfried Leibniz in 1707. So that's another difference from the 18th century to today. Leibniz didn't publish his idea, but described it in a letter, and actually the letter was lost. So we only know about it because of letters other people wrote describing Leibniz's letter. So you couldn't get any credit for a scientific idea nowadays, but apparently in the 18th century you could. Now, these individuals were amazingly diverse in their contributions. And as I said before talking about Young, this was an age where it was possible for one person to know what there was to know about many different fields. Maybe not everything, but many, many fields. So they all had very diverse contributions. For example, Leibniz is probably most known as a great mathematician, the co-inventor of calculus, and as a philosopher and theologian. Euler was one of the great mathematicians of the century, or really of all times. And that's what he's most famous for. But in the 18th century, anyone who was a well-educated mathematician would have been familiar with the physics of the day. That's not true today. Understanding the physical theories we have today is much more of a challenge. And most mathematicians of today, no matter how well educated and successful in their fields, would not have the kind of knowledge of physics that not just Euler, but any of his mathematical contemporaries would have had in the 18th century about the physics of that day. Now, okay, I took this list from Wikipedia, and it sounds crazy, but Wikipedia says that de Moivre was distinguished in all those fields that I've listed. And I listed them indiscriminately. You'll notice that some of those fields made more progress in later centuries than others. And I guess in the 18th century, people didn't have our present view of what fields were more promising. But anyway, he was one of the pioneers of the principle of least action. And Lagrange actually was the one who put it in the form that students learn today. So if, as an undergraduate, you learn the principle of least action, you'll probably learn Lagrange's version. Anyway, these people, instead of adding the potential energy to the kinetic energy to make the total energy E, did the opposite. They subtracted V from T. And then, since the difference T minus V is not independent of time, they averaged over time, or to be more precise, they integrated over time to make the action T minus V. That's essentially our last equation. So they took the definition of the energy and changed the sign, or at least this is Lagrange's formulation, which followed a couple generations of earlier versions. Well, what good is it to take the wrong sign so that you have something that is not independent of the time? Well, they were able to reformulate Newton's laws in a way that sounds kind of crazy. In this formulation, you assume you know where an object was at some early time, say noon on Tuesday, and you know where it will be later on, say at noon the following Sunday. And the question is to figure out how the particle will get from A to B. So we're given that at noon on Tuesday it was here, and at noon on Sunday it will be here. And then, given that information, how did it get from A to B? Well, the answer is that among all possible paths from A to B, the particle follows the path of least action. In other words, the path that, roughly speaking, makes the action I as small as possible. I is the quantity that was, it's not the energy because there was a sign mistake. It's the wrong quantity that isn't independent of time. But the path, if it's true that the particle was here at noon Tuesday and will be here at noon Sunday, then it traveled between them on the path that made the action as small as possible. So this sounds crazy because it contradicts determinism. You're supposed to start with the knowledge of where the particle will be later on, and then check out all possible paths. So it's not like Newton, who says you know where you are and how you're moving at noon on Tuesday, and then I'll tell you where you'll be later on. Here you need to have knowledge about Tuesday and also knowledge about Sunday, and then the goal is to figure out where you were at a given moment on Thursday. So in spirit, it doesn't sound deterministic, but Lagrange and his predecessors showed that this is actually a perfectly good restatement of Newton's laws. But it sounds quite different from Newton's approach, in which at any moment you try to say what will happen next. It involves taking a global look at the whole history. And in the 18th century, a lot of philosophical significance was attached to the principle of least action. De Moivre, for instance, described it by saying that nature is thrifty in all its actions, and claimed that the principle of least action proves the existence of God. Well, okay, that was the principle of least action in the 18th century. We'll zoom forward to the 20th century when quantum mechanics was invented. So it's full of surprises, and it shocked people because it was not causal or deterministic in a traditional sense. So, okay, it shocked people in all kinds of ways, which could have easily made the whole lecture. So, for example, a particle like the electron behaves as a wave. I showed you a computer picture of an electron wave near the beginning of the talk. But for what I'm saying now, it shocked people because it wasn't causal in any traditional sense. Even with the complete knowledge of what there is right now, or knowledge that's as complete as quantum theory allows, you can't predict with certainty what will happen in the future, according to quantum mechanics. Nevertheless, the theory was extraordinarily successful at describing atoms and molecules, and then when the subatomic particles were discovered, it was extremely successful at describing those. And it's much too big a story to try to explain now. But among many other things, quantum mechanics was interpreted by the great 20th century physicists, Paul Dirac and Richard Feynman, in a way that shed light on the principle of least action. So this makes some sense because quantum mechanics isn't deterministic in any conventional sense. And the principle of least action makes it sound like Newton's laws aren't deterministic, even though they are. So it makes sense that the two would go together. Actually, this is what I just said. Since quantum mechanics is not deterministic, and the principle of least action sounds unnatural in a deterministic theory, it's kind of logical for them to go together. What Dirac and Feynman came up with is this. The quantum particle really does sample all paths from A to B, not just the classical paths, but all of them. So I've drawn the classical path, which means the path that obeys Newton's laws, what Newton would tell you is the correct path. But now I've drawn another path. And the blue wiggly line is nothing in particular. It's just a path that the particle could have followed that doesn't obey Newton's laws. But according to Dirac and Feynman, the quantum particle samples all paths from A to B, including crazy-looking paths. So here's a crazier-looking path, but that's also a possible path for a quantum particle. So every path contributes, but with a wildly oscillatory factor. And this, I think this really is my last, mathematical formula. So some will recognize what it is, but anyway, if you don't, every path contributes, but the way they contribute involve wild oscillations, so that the paths that are too far from the classical path end up not being that important. The result of sampling all paths in the way that Dirac and Feynman said is that paths that are too far from the classical path come very close to canceling out. The dominant quantum mechanical contribution comes from the path with least action in the 18th century terminology. So the way the paths cancel out is a lot like interference of waves with which we began. So if you look at the ripples on top of a swimming pool, they're coming from all different directions, probably because somebody splashed into the pool and they're reflected from the boundary and so on. And there will be places where the waves add up and places where they cancel. So the heights, the peaks of the waves are a little bit analogous to what happens when the quantum contribution comes primarily from a path that has the least action, which means from a path that's close to the classical path. But Feynman extended the picture beyond what I've explained. And this, what I'm about to tell you, is actually Richard Feynman's most celebrated contribution to physics. He described interactions of elementary particles in terms of what he called elementary processes, visualized in space-time, at which a particle splits in two or two particles combine. So I've drawn a space-time picture. Space runs horizontally, time runs vertically. A particle A comes in the past, and we assume it was initially at rest. At some given time, it splits into two particles that go out in opposite directions. For example, it might have been a neutral pi meson that after a while decays to two photons. But anyway, in this example, a particle is splitting into two. And if we drew the same picture upside down, or if I simply reversed the arrow and said the time was running down, we'd have two particles coming in and joining into one. So those were the examples of Feynman's elementary processes. Now, not only does a single particle, according to Feynman, sample all possible paths, but when particles are interacting with each other, they sample all possible histories. So here is, roughly speaking, a classical history for scattering of two particles. So again, time runs this way and space runs horizontally. In this example, two particles have come in from the past, and they scatter. Two possibly different particles go out in the future. And in between, there were a variety of Feynman's elementary processes where two particles combined into one, or one split into two, depending on how you look at the picture. So what I've drawn, roughly, is a classical history for scattering of two particles. But Feynman would say that the actual quantum mechanical scattering involves considering quantum histories. And a quantum history is anything. So I've drawn just a wiggly history. So still two came in and two came out after the same elementary processes, but I've connected them with wiggly lines because a quantum particle samples all possible paths. So just to repeat, this is the classical history for particle scattering. And here's an example of a quantum history. But the quantum history could be anything at all. I could have drawn something much crazier, but if you tried to draw something as crazy as a truly generic quantum history, you actually wouldn't be able to see it. It would just look fuzzy. And that's because, so that you can see this, there's a width of all these lines. And that width would be important. If I tried to show the particles zigzagging back and forth like a quantum particle might, you'd end up with only a blur. And in a sense, that's the right answer, because after all, there is an electron wave. So the blur would symbolize the fact that in quantum mechanics, particles behave as waves. Now, the classical history obeys some deterministic equation. The particles travel in straight lines, except when they join or split, and there are rules for the angles when that happens. So here, okay, this is schematic, but I drew straight lines, well, with simple angles, but the angles depend on the masses of the particles and stuff like that. But anyway, this is the deterministic picture, and this isn't. This is, the quantum history is anything. So the quantum history can be anything at all. The only thing that brings some order to a quantum universe is that very wild quantum histories are unlikely because of the way the waves interfere. And that's why we don't see quantum mechanics in everyday life, because at the macroscopic scale at which we live, the wave interference has killed out the things that are too far from a classical picture. So the classical picture works pretty well at a human length scale. So it's again a little bit like the ripples in the pool that can add or cancel depending on how they fit together. Now I want to describe a rather simple sounding rhyme. And then we'll get later to a more subtle rhyme. So we're going to replace a point particle. And well, this is trying to be point particle. Of course, I had to give it some size so that you can see it. But think of it as a particle like an electron that is so small we might as well think of it as a point. But now we're going to replace the point particle with a vibrating string. So I've drawn an example of a loop of string, and if you let it free, it'll vibrate or oscillate in time. So I call it a vibrating string. It won't just sit there with this funny shape I've given. The curvature of the string will cause it to expand or contract in different directions, and it will vibrate. So I'll draw a picture in space-time. So we again think of time as running vertically and space as running horizontally. And what I've drawn is the trajectory of a point particle. So at any given time, the particle is somewhere in space. Later on at this time, it's over here. And that curve, physicists call it the world line of the particle, but that curve is a curve in space-time that describes the motion of the particle. Well, here's the analogous picture for a string. Again, at any given time, we have a loop of string. Later on, the loop is here, and still later, it's here. And as time unfolds, a string sweeps out a two-dimensional surface in space-time, which we call the string world sheet. Now, in both pictures, I drew a smooth classical orbit, because it's too hard to draw anything else, especially in the case of the string. But we're supposed to imagine a random quantum trajectory. So I drew a classical picture, but you should imagine wild wiggles here, and also wild wiggles here, because according to Dirac and Feynman, the quantum particle or string samples all possible orbits or trajectories. So what we're really looking at here is a quantum random one-dimensional geometry in space-time, or quantum random two-dimensional geometry. So in the particle case, a random trajectory is a one-dimensional geometry in space-time, but a random one. In the string case, it's a random two-dimensional geometry. I should warn you, I'm using the word random very loosely. It's random in a quantum mechanical sense, where cancellations are possible, because the randomness involves wave amplitudes that have to be added up before you try to measure them. A classical picture of what randomness means doesn't really do justice to it, and there's also not time today to try to straighten out that point. But therefore, loosely, just say that the particle case has a random one-dimensional geometry, and the string case has a random two-dimensional geometry, where I'm warning you that there's more to the word random than I will be able to explain. But you'll do fine for the rest of the talk just thinking of a random one- or two-dimensional geometry. Well, one question is, why does this naive-sounding idea of replacing a point particle by a string lead to something deep? Well, I'm going to give two answers. We get one answer if we think of a violin string. So by a violin string, for my purposes, I just mean a string tied down at the two ends. And it can vibrate, of course. And here's the simplest way it can vibrate, what's called the fundamental harmonic. But a violin string can vibrate in multiple ways. It could vibrate with this shape, or instead of just going up once, here it goes up and then down. And although I haven't drawn them, a violin string could vibrate with more wiggles, like that. Now, if you only have this form of vibration, you'll get the fundamental tone. This one will be an octave higher, and so on. The many ways that a string can vibrate are responsible for the richness of music. If you want to hear the fundamental tone, you can get a good approximation to it with a tuning fork. But the tuning fork sounds very ugly to the human ear. So we use violins and other instruments like flutes and so on. We don't have symphony orchestras made out of tuning forks because people don't like the results. So to the human ear, the beauty of music comes from the interplay of the different harmonics, the different shapes that the string can vibrate, or analogous statements for other instruments. Okay. That's the answer for stringed instruments, but there's an analog for all the other instruments in the orchestra. Well, likewise, the strings I'm talking to you about can vibrate in many ways. But rather than a basic tone and its higher overtones, for this kind of string, the different forms of vibration correspond to different elementary particles. So if string theory is correct, the unity of the elementary particles arises because the different elementary particles are different forms of vibration of one basic string. So if string theory is correct, all the elementary particles, the ones you know about and the ones you don't know about, if you're not physicists, are different states of vibration of the same string. So the electron, the muon, the up quark, the photon, the neutrino, and so on, are different forms of vibration of the string. So one answer to the question of why this leads to something deep is that because a string can vibrate in many different ways, it forces us to unify the elementary particles and their forces. But there's another answer that we can see if we rethink Feynman's elementary processes. So remember, this was the basic picture in space-time for the simplest elementary process, where one particle breaks into two. Time was running vertically and space horizontally, though I haven't repeated that here. And here's the analog of that process in string theory. So one string came in the past and it broke into two. And roughly speaking, this picture does the same thing this one did. If this describes a particle going to two other particles, and if the particles are really strings, then this still describes a particle going to two other particles. But there are some important differences between the two pictures. In the string theory case, something happened, but you can't say when and where it happened. So in the particle case, this was the definite space-time event at which something happened. But in the string case, any small piece of the picture looks like any other small piece. I've sometimes been asked the following question. In the string case, was there not a last time at which there was one string instead of two? And there was in any given coordinate system. But Einstein taught us that a surface of constant time isn't the same for all observers. So although I might regard this as a surface of constant time and say something happened here, somebody else would have a different surface of constant time and would identify a different moment where one string broke into two. The important thing here is that any small piece of this picture looks like any other, but here there is a definite moment that's different from the others. So this is the beginning of the fact, it's the first sign of the fact that familiar concepts of space and time become murky in string theory, somewhat like the way like quantum mechanics, made a lot of the notions of classical Newtonian physics become a little bit murky. So in the passage to quantum mechanics, there was an uncertainty principle that says that you can't know exactly, you can't have all the information you have classically, where you know where a particle is and how it's moving at the same time. In the case of string theory, you can't pin down space and time in the familiar way. So in the particle case, there's a definite space-time event. The string case still describes particle interactions, but without a definite space-time event. And while that is probably a rather naive interpretation of this picture, it turns out, supported by many interesting calculations done by now over a period of decades, that this is a first hint of something very basic, that the space-time concepts of physics as we know it today are modified in string theory. Going from the point particle to the string gives an inherent fuzziness to space-time in a way that's a little bit like how quantum mechanics gives an inherent fuzziness to the orbit of a particle. So I've explained a possible rhyme. String theory repeats the established structure of physics, but with particles replaced by strings, and one-dimensional particle trajectories in space-time replaced by two-dimensional ones. The particle trajectories are world lines in the language of physicists, and the string trajectories are world sheets. But this rhyme is not the deeper rhyme that I had in mind with the title of this talk. The deeper rhyme concerns the other great revolution in 20th century physics, whose centennial we celebrate this year. This is Einstein's theory of gravity, which he called general relativity. Newton had viewed space-time as simply an arena in which events unfold. Einstein taught us that actually a big part of the story is how space-time unfolds. So Newton had written equations that describe where the particle will be later on if you know where it is and how it's moving at the initial time. Einstein did the same thing for space-time. The Einstein equations tell you what space-time will look like later on if you know what it looks like and how it's changing at an initial time. The only trouble is that Einstein's equations are describing four-dimensional geometries, and I couldn't think of any reasonable way to draw four-dimensional geometries for you. To explain in another way the difference between Newton and Einstein, Newton said that the planets go around the sun because there's a gravitational force pulling the planets to the sun. So according to Newton, there's a force from the planet toward the sun that causes the planet to keep bending in the direction of the sun. Although by solving his equations, Newton discovered that the planet never gets there. It's always bending toward the right, that means in the direction of the sun. But it's got enough energy so that it actually stays in the orbit I've drawn. Einstein's picture of the same, description of the same story is different. Einstein said that the sun curves the space-time around it, and the planets are simply going on the straightest path that there is in a curved space-time. So it's very important that what is curved here is space-time and not just space. So Einstein taught us that we have to include time along with space on an equal footing. And if you try to do this, assuming that space is curved and not space-time, it really doesn't work. Supposedly, the 19th century mathematician Bernard Riemann, who invented the mathematical tools for describing curved spaces, had the idea that gravity resulted from curvature, but he assumed it was curvature of space. And then it doesn't work. Einstein, before he developed his theory of gravity, had learned to treat space and time together in his earlier theory, the special theory of relativity. And then, so when he tried to interpret this picture in terms of curvature, it was the space-time that was curved, with time playing a very essential role. And then in that context, he was able to show that the planet is simply moving on the closest thing there is to a straight path in a curved space-time. So it works beautifully, and it leads to the expanding universe, black holes, gravitational lenses, and all the rest. Well, I should say even farther back, it leads to very very nice success in describing details of motion in the solar system, but also to these more exotic things. So for instance, this is a picture from the Hubble Space Telescope. And the arcs here come from general relativity at work. They're images of very distant galaxies that have been distorted gravitationally by the gravitational fields of more closer galaxies. So you can, in this type of picture, of very distant galaxies that are very massive near galaxies with much more distant galaxies nearby in the sky, the curvature of space-time produces obvious effects of greatly distorting the images of the distant galaxies. So Einstein's theory works beautifully both in the solar system and plenty of things that are more exotic. But from a modern point of view, there's a problem. Well, Einstein discovered his theory a century ago. This year is the centennial. Quantum mechanics was also discovered roughly a century ago. And this means that we have to treat general relativity quantum mechanically. Just as quantum mechanics means that the deterministic classical orbit of a particle has to be replaced by a random quantum orbit, so is the same true for the geometry of spacetime. So what it means to treat general relativity quantum mechanically is that instead of the classical spacetime that Einstein envisaged, where if you know what it is at the initial moment, you solve his equations and learn what happens later, the quantum picture would somehow have to replace Einstein's classical geometry with a random quantum geometry. But we don't really understand how to do random quantum geometry in 4 dimensions. So remember, 4 is the right dimension because Einstein included time. So space-time has the 3 obvious dimensions of space. Einstein included also time in the picture, so it's a 4-dimensional space-time. And with our familiar physical and mathematical ideas and techniques, we're not able to describe 4-dimensional random quantum geometry. So as I said already, here you have to bear in mind that 4 is the right number because Einstein taught us to include time. But 4-dimensional random quantum geometry does not work along any conventional lines because the nonlinear mathematics that Einstein used in his theory clashes with the requirements of quantum theory. So, this is a conundrum in physics. So the 2 best theories of the age are quantum theory and general relativity. And there has to be some way to make them work together because, for example, so we apply general relativity to stars, but the stars are ultimately made out of atoms and subatomic particles. We know that quantum mechanics works for the subatomic particles. It doesn't make sense to have one theory for the individual atoms making up a star and a completely different theory for the star. There has to be some way of combining the 2 theories to make them work together, but along conventional lines that doesn't work. Well, although we don't really understand 4-dimensional random geometry, we found good use for 1- and 2-dimensional random geometry, as I've explained. So the random 1-dimensional geometry is an alternative way to talk about our standard quantum theories, the theories developed throughout the 20th century. And the random 2-dimensional quantum geometry is the framework for possibly unifying the particles and forces in the context of string theory. So actually, this is what I just said. The 1-dimensional random geometry is another way to describe well-established physics. And that's one of nature's rhymes. So quantum gravity, whatever it is, would involve 4-dimensional random geometry, and we don't understand it. But other areas of physics that we really do understand can be described in terms of 1-dimensional random geometry. So this is an example of nature repeating herself with similar structures in different places. The 1-dimensional random geometry that Dirac and Feynman used to describe a quantum particle, or the 4-dimensional random geometry that would hopefully reconcile Einstein's theory with quantum mechanics. But there's a much deeper rhyme if string theory is correct. Then, first of all, random 2-dimensional quantum geometry is key to unifying the forces. The one-dimensional random geometry lets us describe our quantum theories of today, but the two-dimensional case forces us to unify the particles and forces because of the many different ways that a string can vibrate. But there's something more to this, which is the deepest rhyme I have to offer you today. It turns out that one of the states of a vibrating string, so remember, for a violin string, this is the basic way it can vibrate, and this is the second, and there are many, many more. Likewise, the strings used in my kind of string theory can vibrate in many different ways, but one of the states of the vibrating string turns out to be a graviton, a basic quantum unit of the gravitational field, analogous to the photon, which is a basic quantum unit of light. To say this differently, when we unify the elementary particles and their forces using string theory, we get general relativity for free as part of the bargain. So if string theory is correct, it basically means that two-dimensional random quantum geometry on the string world sheet, which we know how to do, although it stretches our understanding. We know how to do this, but it's relatively close to the frontier of what we know how to do. It's the key to a new kind of four-dimensional random quantum geometry, which we need, but otherwise do not know how to do. And that's the deepest rhyme or potential rhyme that I have to offer you today. Thank you.